Good evening, everybody. This is Obi-Wan Pez for Simplix Pachinko. We are going to be doing some math tonight, followed by some Elite Dangerous because a big update just dropped. And everybody's going crazy. So, we will split the stream and do some math at first, and then go out and play some Elite Dangerous after. Because what the crap, everybody. What the crap. Alright. I don't think anything particularly interesting has fallen in my lap the last week here, but can again take a look at some other stuff that we got in here. Let's see. Look at some moist, I think. All right. Alright, so in chapter 1, what we were mostly concerned with... Let's not do that. Blayland, yes. And again, it's all coming down to just plopping some limits down there to say, well, we're not really taking a finite integral. This one's, going to have an infinite value, or the limits are going to be infinitely large. So it's just have fun with the, limit definitions. Yes. So, to tonight's board. All right, here we go. So, differential equations. At its very, very most basic thing, you're going to hate me for this, it's an equation with a differential in it. Now the question really is, what's a differential? I know, I'm such a jackass. What's a differential? So a differential is going to be any particular term that lets you know that there was a derivative that was taken here. So most of the time when you see them, it looks something like dx, dy, dt, d theta, like all this stuff. And like I said, most of the time you're going to see it in this form. Now it is possible, and very likely, that the way that it's written for you is going to be something like dy dx is equal to 5x plus 7. Or in other words, a dy dx is equal to some sort of function of x. Goodness. There's a thunderstorm. All right, so very generally. And then very generally, the way to solve this is going to be to take the integral of your dy dx and the integral of your f of x dx. Now this becomes an interesting problem. Ooh, nice. This becomes an interesting problem. A, where did that come from? And B, why isn't that the same as over here? Hey, Megalomorph. Yes. Differential equations most definitely require that sort of notation, because otherwise you have no idea what anyone else is talking about. You might have a very good idea of what you're talking about, but the problem here is communication. Alright, so what I would suggest is actually not do this. Generally, when I do differential equations, I say turn it into an equation where there are differentials in each part. So here what we do is we do something called separation. It's not quite separation of variables is something else, but we'll call it separable. So this is a separable differential equation. By that, I mean that we could take all of the y stuff and put it over here, and all of the x stuff and put it over here. So for instance, in this particular case, you multiply both sides by dx. And we end up with a dy is equal to f of x dx. And then we could take the integral operator and put it on both sides. Goodness. You know, thank you, but at the same time, then you wouldn't get any credit for it. Granted, if you did take it from me, it would be able to, like, you know, take a clep or something, but... Alright. I'll tell you what. I'm not teaching it this semester, but taking online classes might be a thing. Alright, so anyway... Oh, don't dox myself. Don't dox myself. So, what I would suggest is then taking the differential operator, or sorry, taking the integral operator and put it on both sides here, and now it has a natural variable that goes with it already. So I absolutely love this particular form of differential equations, where you can separate them so that all of your dx and dy stuff are on their own side. And then you can just do this, where, again, take the integral operator of both sides. Alright, so on the left, this ends up becoming y, technically plus c, and we'll just let it be c1 for the moment. And over here on the right, this ends up being whatever big F of x is plus c2. Alright, and then we shift this over here, so that we get y is equal to some big F of x plus, we'll just call it c. So the constant c2 minus c1 is just going to be another constant. So we just let it be another constant, we call it c. So that's really the shortcut for this is, you know, don't make multiple constants. Just... Oh no, which one do you mean, Megalomorph? So, sort of. Yeah. F is just considered the antiderivative of a little f. So, we defined this at some point to say that if you're going to take the integral of some function f of x dx, then usually we call it big f of x plus c. And it's just basically yeah, notational stuff. That was in Calc 1, so I mean... Yeah, thank you. Convention. Yeah, fundamental theorem of calculus says that if we're doing something like ddx of taking the integral from 0 to t of f of x dx... I probably have that wrong. Right. Yeah, I have that backwards. It doesn't really matter because it's all just, again, convention and notation. Yeah, Megalomorph, correct me if I'm... So this was saying that if we end up taking the integral from 0 to x of f of t dt, and then take the derivative with respect to t, maybe, then we just end up getting back to where we started, ddx. Yeah, I figured I was going to mess that up somewhere. So that's your fundamental theorem of calculus, which basically just says that integrals and derivatives undo each other, and Megalomorph can be much more rigorous in that if he so chooses. How crazy is Euler method? Not really all that crazy. It's actually not bad at all. Alright, so we'll get through a little bit more of differential equations and then we'll hop over to Euler method. So generally speaking, you're not going to get something quite as nice as this separable differential equation. You're going to get stuff that goes all over the place, and it ranges all over. However, for most of what you have here, yeah, it's not even technically differential equations in terms of, like, you know, solving the differential equation. It's finding a nice approximation, and you don't have to use like the integral methods in order to get it. So that's also kind of nice because Euler's method and all other numerical analysis. And you're going to come back when you see Taylor method and you're going to be like, what the hell? So anyway, there's all sorts of approximation numerical methods that you can use. Euler's method is like the most basic one. Calc 3 is not really all that bad. I found it basically like starting Calc 1 all over again. You're doing vector calculus, and you're trying to figure out like all of these partial derivatives, which are taking derivatives in, you know, higher dimensions, and saying like, I only want to talk about the derivative in this particular direction. So my x direction. I don't care about the y direction. I don't care about the z direction. But the function has all x, y's, and z's. and maybe temperature and time and like all this other stuff. It can have as many variables as you want, but all you care about is how does the rate of change look as I change one variable. So as I go along x, what is it? How does it change? Yep, series and sequences. I see. Yeah, every school does it slightly differently. My state kind of, like, finally mandated that we, like, straighten up all of this stuff. They kind of let us do it, which was nice. But they were like, look, all of the different numbers and, like, craziness and stuff like that, you can't do this. You've got to clean it up. And so we spent a good couple of years, like I was on that committee, spent a good couple of years straightening out everybody's calculus and then pre-calculus stuff. I see. Interesting. Okay. So they might actually use series and sequences to solve differential equations in your Calc 3. It's possible. Usually we leave that to the actual differential equations class, but, you know, everybody does it differently. Okay. So for differential equations, very generally, you've got different types of differential equations that you could have. This is the super easy one that you're going to be doing for Calc 2. If you get into the actual differential equations class, then you start getting into all the crazy stuff. So we've got, let me see if I got my notes here. I think this is the right book. Yes, okay. All right, so there's all sorts of ones, like I said. Dy dx is equal to function of x was nice and easy. Dy dx is a function of y is also nice and easy, but for a different, slightly different reason. Linear algebra discrete, yeah. You know, the Euler's method style differential equations would actually do you a lot better once you get into stuff like, if you're at all interested in it, neural networks and AI. Because we ended up using differential equations a lot in order to do numerical approximations for weighting calculation or weighting changes and stuff like that. So it was really cool. Okay, so we've got dy dx is equal to functions of both x and y, which can be complicated depending on what f is. So this is where it starts getting into all sorts of crazy stuff. Right, these two are easy. So there are certain classes that are taken mostly for, like, knowing and understanding the algebra and understanding how the relationships work between these things. Yes, it may be that, like, particular integration methods and things like that are not super useful, but at the same time, if you're going to have a well-rounded student who needs to be able to do literally anything, even if everything they do is 100% by computer, right? There's got to be someone somewhere who understands this stuff at a fundamental level. And yes, maybe that should just be the math majors as a whole, but you know, understanding the integration techniques and how all this works then can allow you to start building up into oi. Allow you to start building up into the higher mathematics classes. So again, does it need to be every single student who takes Calc 2 and does all the integration methods like trig, substitution, and all this? I don't know. I mean, Megalomorph has a better idea, being that he teaches well, more varied college students than I do. I teach college students who, you know, they do their first 2 years and then they leave. Well, again, is it really trying to teach you those individual things and that's it? Or is it that we're trying to teach you the broader strokes of mathematics to get you to try to understand, like, how math works? What kinds of relationships exist? Because there could be a whole bunch of stuff that you look at, like the, you know, integration table, and you're just like, what the crap? How did that happen? And sure, you can go online to Paul's or whatever and get a proof of it, but at the same time, it is nice in some ways when you can figure out an integration just by yourself. You don't need, you know, Wolfram Alpha or whatever to do it for you. I don't know. Maybe that's enough pontificating for a while, but nope. All right. This one here is not something that we ever deal with in this class. Again, mostly it's taken to be like... This is mostly done in the differential equation stuff. This starts getting into partial differential equations, and that's a whole nother can of worms that we don't want to open up on this stream anytime soon. But these are all differential equations that Newton solved. Granted, I'm using Leibniz notation because it's far superior, and anybody who would like to say otherwise can fight me. Call me in front of the Royal Society. And then have Newton be the president. Dick. So Alright, so anyway, yeah, that ends up being mostly partial differential equations that you start getting into over there. And then there's a whole lot of other stuff that Leibniz, that the Bernoulli brothers, eventually Daniel Bernoulli, Lagrange, Laplace, and many other French people were able to get into and solve differential equations by various methods. And so there's really cool stuff that get into all this. So for differential equations, the most useful methods end up being like, okay, well, see if you can make it separable and then solve it. The easiest ones are basically, this is the textbook stuff in Calc 1, like flip to the back of the textbook and look at the integral table. That's it, right? If dy dx is equal to this function, then its integral is this. And so, you know, y is equal to this. Down here, this gets a little more complicated. These end up requiring you to make this dy over f of y is equal to dx. And so now we end up with something here which may or may not turn out to be nice in many simple cases, like a linear function, right? If f of y is some sort of linear function, this is just a natural log, And so y would be equal to an exponential because you're going to raise both sides, or raise e to both sides. All right, yeah, fair. But, I mean, it is far superior to the Newtonian notation of trying to take a fourth derivative and putting dots over the top of it. Oh, Megalomorph, when you're on again, I probably need to ask you about, what's his face? Dr. Grenfeld's tensor calc stuff. I'm way back at the beginning of this book, so it doesn't matter. But I'm just looking at I was looking at the partial derivative chain rule, and it was just like I can't even. Like, I get the rule, but trying to prove the second derivative based on the first, it was just, yeah, it's getting pretty ugly. So I have it in here on video on demand somewhere, probably last week or week before. If it's 2 weeks ago, it's probably almost gone by this point. Anyway, so, Blandland. So we go into here and we say, okay, let's suggest that we have a differential equation that we cannot solve. So this is like y prime is equal to yeah. All right, so for Euler's method, the important part here is to get this in terms of y prime is equal to, or dy dx equals some function. And in this case, we can have it be a function of x or y, or both. It doesn't really matter. Most of the easy ones are going to just be a function of x to be able to get you used to doing things. And yeah, most of the time you're not going to have a y to deal with also in there, because it gets kind of nasty. But for a simple one, we'll do y prime is equal to 3 natural log of x, because I'm evil, minus 7x plus 2. Okay, now I'm going to want to look at this to see where a convenient location to put my values is going to be. Alright, so I'm going to graph this. Okay, cool. So nice. So I'm going to want to take this at x equals 0.5. I'm going to take delta x to be 0.1. So what you're going to do is make this into a split up here. This function, more or less, looks like this. So what we're going to want to do, all right, 0.5 is right about here. and we want to do 0.1, and so totally to scale. Yeah. All right, what we're going to want to do is say we're starting here, and we want to be able to approximate this curve. Now, the curvier a section is, the worse the approximation is going to be. You want something that has second derivatives that are really close to 0. Like, for instance, this area. That would be pretty nice, because this area here is almost a straight line. And so doing Euler's method on it will be practically trivial. But, of course, as the case may be, the curvy sections are the ones where you're most likely going to have approximations that are needed. So, of course, it's going to be awful. All right, so let's do a quick little table here. Okay. I'm kind of wishing my TI-80 3.4, whatever it is, had batteries. I got the 89, which is fine, but I'm not as good with it. Okay. So anyway, this is now 1.0 here, and we just want to be able to approximate. Let's say we want to approximate y at 1. Now, for instance, we may not be able to do y equals 1 or x equals 1 for some reason. It might be a singular point. It might have some other issues that are going on with it. Again, for whatever reason, we may not have... Oh, right. Never mind. Duh. I can't solve this. This one's actually separable, so again, it's not hard to solve this differential equation. But if we did some extra stuff with it, we would be able to make this impossible to solve, to get an actual value for the function y. And especially at y equals... Sorry, y is 1. No, x is 1 for the function y. We have y prime, we just don't know what y is. We don't know. Right, bear with me. Pretend that we can't find the integral. So, if we totally can't find the integral of this particular function, what we're going to do is say, okay, let's approximate what would happen if we took the function value that we know exists, which... I didn't get this, hang on. Yeah. Crap. Because I definitely know what this integral is. Let me... Okay, so I'm gonna get this, plug that in, and right, I mean, I'm an idiot, of course. The solution could literally be whatever we want, because it doesn't actually matter. Oh. Okay, hang on. Okay, couple of things. One, this is really important. This is y prime versus x. I'm totally forgetting all that. Okay, so let's graph the other function. Really? What did I do? There we go. All right. Can we turn this one off real quick? Ah, there we go. 4. And then we graph it. Okay. Alright, so this particular function looks like this. And this is y versus x, rather than y prime versus x. Runge-Kutta. Oh my goodness. we had to prove the Runge-Kutta. I don't remember which order that is now that I'm looking at it. I guess it's just the, you know, standard one, possibly 4th order. Anyway, so if we get the approximation of this thing, we know that the, alright, let's do y2 of 0.5 is, okay, so we know negative 2.41472. There's probably more to that, but you know, yeah. 72077 08399. All right, this just keeps going on forever. So, depending on how accurate we want this to be, we could probably round it to here and just be satisfied with, you know, this is close enough. Alternatively, if you have that in your computer, you know, in your computer calculator or whatever, keep it. You know, keep all of the decimal places and then just round it like on paper. Just, you know, say that that's what you're doing and tell your teacher, okay, well, we're rounding it to like 6 decimal places and that's all I'm ever going to show you. But we want to be able to have it out to as many as the calculator can carry. That's just being a mathematician. Now, granted, you could decide you wanted to instead figure out significant figures and like how many significant figures do we actually need, and then eventually work out what's important out of this. But quite frankly, I don't care. I will keep it as an exact value in my calculator until the very end, and then I'll round it and say, yeah, we'll deal with that later. So, the point that we're looking at is 0.5, comma, negative 2.41472077008, etc. We want delta x to be 0.1. What we're going to do is we're going to say, okay, we're starting here. This is the point where we're going to start. We're going to take the derivative at this particular location, which is denoted by a tangent to that particular line. And then we go out to wherever this is. And then we take the tangent here. Nope, it's not 45 degrees. Come on. It's totally 100% accurate. All right, then we take that and go out to here. And then we take the derivative here at this particular location and find out that it has a slope like that. And then at this location, we're going to take the derivative here, which has a slope like that. It's going to be a little bit steeper than 45 degrees. Whatever, cool, it's locking into place. And then we take a, next one here, and this derivative is much steeper, so it goes like this. And that goes for a little while. So it basically starts doing this like segment after segment after segment. It becomes more and more and more inaccurate, naturally. And that's going to be all numerical methods. All right, Megalomorph, see you later. Right, it's no matter what numerical method we're using, it's going to compound the errors from the previous iteration and then just make the new iteration worse. So the Euler's method is like a quick and dirty way to do this. You can program it into a computer, it'll do it fast, it'll get an answer, which is at least reasonable-ish. And again, the higher the second derivative value is, the worse it's going to get. So again, if your second derivative is really small, this is probably good enough. It just won't matter. And here's the other thing. If you're doing Euler's method with a computer, and you can get your delta x to be like 0.01, 0.000001 or something like that, then who cares? It's going to take like a few extra seconds, but you're going to get something that's just as accurate as like, finding a really complicated method like Runge-Kutta. We'll talk about Runge-Kutta another time. But basically, it ends up being like a lot more work to get one iteration done, but it's way more accurate. Okay, so here's what we're going to do. We're going to take a series of linear approximations. So if you remember your linear approximations, this is basically like Newton's method, where we say, okay, we're going to take y equals, or like y1 is equal to m1 times x1 plus b1. And then when we do the next segment, we're going to plug in a new value. Let me use point slope, because point slope makes way more sense in this. M times x1 minus x0, that works. So here we have x0, y0. Okay, and then this is going to be plus y0. Okay, so what we do here is we say, all right, let's plug in the values that we had up here. Our delta x is going to be 0.1, so x1 minus x0 is the difference between the two x's. Well, that's just delta x. So m1 times delta x 1, because technically you could have a delta x which is different on a certain step. So your delta x can be anything you want it to be. in linear approximation, it's just delta x, and it's always going to be the same delta x. M1 is now going to be, instead of just M1, we're going to call it f prime at x0 times, and again, this is just delta x1 plus y0. Or in this case, again, we didn't use f, we used y. It's all good. So y prime at x0. Well, we have x0 is 0.5. Right, or just the function y at x0. We could play around with notation all night. Okay, so y1 is going to be equal to y prime at x0. Well, x0 is 0.5, so this is y prime here. So this is going to be 3 natural log of a half minus 7 times a half plus 2. There you go. There's your y prime at x0. Multiplied by delta x is just going to be 0.1 plus y at x0 is this number. This is our negative 2.4147207708399. So y1 is going to be very approximately this nasty thing. So we take that number, we add to it 0.1 times. That is y1 at 0.5. Okay, and this comes out with a number that is not terribly far away. Not surprising. This is going to be a negative 2.77 266 4925 0079. And again, this keeps going on. So y1 is going to be this value. Now we just cycle this through and we say, okay, now we want to do the same thing. So now we got to do y2 is going to be it's going to be equal to y prime at x1 multiplied by our delta x added to our y1. And again, delta x2 technically, but you know, it's going to all be the same stuff. So this is now going to be 3 times the natural log of 0.6 minus 7 times 0.6 plus 2. All that multiplied by 0.1. And then we are going to add that to this negative number here, plus a negative 2.77266492.5, etc. So y2 is going to be approximated by this nasty thing, which again, all we have to do is take this value, add to it y1 of 0.6 multiplied by 0.1. Okay, now this has a negative 3.1459, nice try, 126.121.377. Okay, and then again we do the same thing where we want the value at, this is 0.1, nope, this is going to be 0.6, this is 0.7, now we do 0.8, x equals 0.8. All right, so our approximation is going to be y sub 5. So y3 is equal to y prime at x2 multiplied by delta x3 plus y2. And again, it's going to be approximately equal to parentheses 3 natural log 0.7 minus 7 times 0.7 plus 2 times 0.1 minus 3.1459126121, etc. And so our y3 plus y1 of 0.7. Boo. Times 0.1 ends up with a negative 3.5, 4, 4, 29, 15095, 3193. This is not terribly exciting, and like I said, you just get a computer to do this faster, right? Just have the computer do this. It's not difficult. It'll take you about 5 seconds of programming. The much more difficult ones are like talking about the reverse Euler and Runge-Kuta's like sort of difficult, but yeah, there's just a formula. All right, y prime at x3 multiplied by delta x4 plus y3. So that's going to be equal to, here again, 3 natural log 0.8 minus 7 times 0.8 plus 2 times 0.1 minus 3.5429, and I'm just going to ellipsis all of this stuff. So we get this negative 3.54 plus 0.1 times y1 at 0.8. All right, this is going to be a negative 3.96985816007 and more after that. And then finally, y5. Is going to be y prime at x of 4 times delta x of 5 plus y4. Okay, which is again going to be 3 natural log 0.9 minus 7 0.9 plus 2 parentheses times 0.1 minus 3.9698, and so y5, finally we're there, is going to be that previous number plus 0.1 times y1 at 0.9. Alright, so we get a negative 4.431466315411. Okay, so this is our value. This is what we've got. So y at 1 should be approximately equal to negative 4.4315. I don't know, somewhere about here. So if we go into our calculator or whatever and I want y2 at 1. This is going to get me exactly, interestingly enough, what's y2? Yeah, okay. Okay, so y at 1 is exactly equal to 4.5 according to what I've got here. With a delta x of 0.1 and working this out, right, our actual value is 4.5, but the Euler approximation value, negative 4.5. Yeah, all right, cool. Oh, right, because the natural log is 0 at... Man. All right, negative 4.5. All right, so then we can look at this and say, how good is this? So this is going to be our negative 4.5 minus negative 4.43146631, etc. Absolute value divided by negative 4.5, right, over actual. Okay, take this value, subtract negative 4.5 from it, take that, and then divide 4.5. We get a value of 1.523%. So, not bad. And again, something simple like this, it would work out pretty well. So for more complicated functions, obviously this is going to start getting a bit out of hand, and you're just going to want to get the computer to do it for you, because it's, like I said, it just gets really ugly really quick. Alright, so here's one we've used for homework in the past. Y prime is equal to 2x squared plus 3y squared minus 2 for initial value, y of 2 equals 1, and delta x is equal to 0.05. And this is find find y at 2.2. Now, because this differential equation is not separable, and you might be saying, well, it looks separable, you just take the y's and move them over. That's great, but the problem is that when you return this to the style of differential equation, which I do, which is, again, dy dx is equal to this function, your first step would be to multiply by dx on both sides to get it through. So this would be dy is equal to 2x squared dx, which is fine, that's differentiable, plus 3y squared dx, which is not differentiable. All right, minus 2 dx. All right, when you're mixing variables like this, that creates a problem. So we can't do that. There are other methods which will work on this just fine. But this particular one right here is not going to cut it. So, unfortunately. So what we have to do is say, all right, for now, we've got to take this numerical integration. We've got to figure out what y at 2.2 is going to be. And for that, we can use Euler's method, which, again, just using the same stuff we did before, say that y1 is going to be equal to, again, y prime at, in this particular case, it uses both as an input. So this is going to be our x0 comma y0 times delta x plus y0. So here, y1 is going to be approximated by, and again here, this is going to be y prime is 2 x squared, x was 2, plus 3, y was 1 squared, minus 2, multiplied by delta x is 0.05, 0.05. Okay, and then plus y0 was, again, 1. So y1 here is going to be, this is 4 times 2 is 8, plus 3 is 11, minus 2 is going to be 9, times 0.05, plus 1. So y sub 1, which is going to be y at 2.05. All right, so y at 2.05 is going to be, this is 0.45 plus 1, so 1.45. Okay, there's one step. y2 then is going to be equal to y prime at x1, y1 times delta x plus y1. which is no, right. Our x value was off, but anyway. So we use the previous x value in here. This is going to be 2 times. X squared is going to be 2.05 parentheses squared. Okay, and then plus 3 times 1.45, which is our previous y value, squared, plus, nope, minus 2. Times 0.05 plus 1. 1.45, sorry, previous value. Okay, so y2 is going to be approximated by all of this junk. So, two times 2.05 squared plus 3 times 1.45 squared minus 2 times 0.05 plus 1.45. 2.085625. Nice. Okay. 2.085625. And actually that is an exact value. It's out of 64ths or whatever it ends up being. Okay, so this one is y at 2.1. Okay, y3 is equal to y prime at x2, y2 plus y, nope, times delta x plus y2. Okay. So this is going to be equal to, again, twice multiplied by our previous x value was 2.05, so now it's 2.1 squared plus 3 times y squared is that 2.085625 squared minus 2 times 0.05 plus the new y value 2.085625. Okay, and the approximate value out of this is going to be a bit longer. All right, 2 times 2.1. That number squared. .0791 approximately, so yep, got that one. 3.0790997460938, etc. So y3 is the same as y at 2.15. Okay, and y4 is equal to y prime at x3, y3 times delta x plus y3. So this is going to be, again, twice 2.15 squared plus 3 times 3.079 099746, etc. squared minus 2 times 0.05 plus r 3.0790997 and more stuff after that. And update 2.08 to be that number. Okay. And our last number here, which again, y of 2.2 is going to be approximated by the value 4.8634780330530531. So again, however accurate you need this to be, that's your number. I'd suggest we can work out exactly how much we need, or like how accurate we need this to be. We could also, that's not what I wanted. Could also get Wolfram to work out what the value should be here. So this is going to be 2x squared plus 3y squared minus 2 for y of 2 equals 1. Alright, so we have our initial condition. That's what we end up getting. Okay, so this is y equals 1 over 7 minus 3x. Alright then. Okay, so then we wanted to know what y at 2.2 was. So 1 over 7 minus 3 times 2.2. It's actually not difficult at all. Is equal to 1 over, this is 7 minus 6.6, is 1 over 0.4. 0.4 is 2/5. So this is going to be equal to 5/2. So the actual is 5/2. That's really far off. If that's true. Goodness. So singular point at 7/3, which is 2.6 repeated, right? No, 2.3 repeated. Okay, yeah. So our second derivative really got big. Pretty close to 2. So yeah. graph window. Okay, yeah. So basically what we've got is a value that goes 1, 2, 3, 4. At 2.3, we've got a singularity. X equals 7/3. And we wanted a value at 2, which was 2, 1. And then we wanted this to approximate what values we were going to get. So this is like 0.15 out here. Is it going like that? Oops. Doesn't do that. So, very rough sketch. Something like that. So we wanted to figure out what all the derivatives were along this curve over this tiny little section here. But again, because the second derivative is getting so large, we're finding the singularity value. Well, that kind of sucks. Alright, Blandlin, I hope this helped. And if anybody has any more math questions, let me know. Otherwise, I'm going to switch over because we just had a crazy update with Elite Dangerous, and oof. I think I'd like to get into it. So we're going to try to find... So, some crazy stuff happened in Elite. Basically, the Thargoids, who are a race of aliens who live on ammonia-type worlds, have been, like, getting battered by humans due to the fact that we started encroaching on their space and then started stirring up ancient technology belonging to a species called the Guardians. As it turned out, the Guardians beat back the Thargoids in order to, like, we don't know exactly the terms of the war or whatever was going on, but back in the old days, they beat the Thargoids back and completely destroyed them. So people have been rallying around the Guardian tech and being like, they're going to help us win the Thargoid war. And this guy called Salvation decided that he was going to rear his ugly head after 200 years of being dormant. Yes, I did say 200 years of being dormant. Or something like that. And what he did was he decided to build a super weapon. And as you can imagine, only the best people have super weapons. So they decided to build a super weapon. They then built the super weapon with the help of the player base. Meanwhile, Psyche, Malik, Selene Stardragon, Psychit, and like a whole host of other Elite Dangerous streamers were like, no, what are you doing? So everybody's been like, oh, you Thargoid loving whatever, and then everybody's saying like, no, you're just doing a very bad, stupid thing. Don't do that. So, I'm going to start up the main game, and anybody who has math questions, you can still ask. I will still have it up in the background anyway. But I'm going to switch scenes. Don't panic.